Hi, this is Tony Tamasi with NVIDIA, and I'm here to talk to you about Quake II RTX and an advanced form of ray tracing called path tracing. What you see here is actually an overview of the path tracer that we've implemented in Quake II RTX. We're going to start from the eye, or camera, and follow the primary ray as it traverses into the scene. In the game, we're now showing just the primary rays, but in this case with a small ambient turn, because of course, without ambient light, the scene would be black. So we're going to follow that primary ray as it intersects with that mirrored surface. Our primary ray goes through that surface refracting or bouncing off that surface, which would be reflection. What you see here is the impact of those reflection and refraction rays as being traced in the scene. The reflection is showing something behind the camera, and the refraction is showing that kind of warped or distorted part of that mirrored surface. One of the properties of our path tracer is that it random samples or stochastically samples between a variety of lights. So we're going to follow that reflected ray as it intersects with the surface. First, it will compute which light it needs to sample from. The second thing it will do is it will determine whether it's in light or shadow. So we've shot a ray from that surface, we've sampled the local lights, so you can see the impact of both light and shadow in the scene now. In addition to sampling from the local lights, we of course sample from the sun. So in the same way that we shoot a ray towards a randomly sampled local light, we do the same things towards the sun, and again sample both light or occlusion for shadow to determine the proper total lighting picture for that pixel. If you look in the mirror, you'll see kind of a bright yellow light in the back. That's those direct rays being cast to the sun and their resulting influence on the scene. So the next thing we're going to do is compute the indirect bounce. By bouncing light, we accumulate indirect lighting information, which is that next level of detail for realism. As you can see, as we toggle back and forth, this effect is more subtle. The bounce by itself doesn't have a large contribution, but the impact will be much greater when we start computing the indirect sunlight later. So now that we've bounced our ray, the first step is to compute lighting from that indirect surface. So we're going to compute local lights first, again randomly sampling them, and then computing light and shadow in an indirect manner. As we toggle back and forth between the previous step, if you look at the object in the corner or the walls, you're seeing it accumulate a bit more brightness, and that's the impact of that indirect local light. The final step for our path tracer here is to compute the indirect sunlight. So we take the bounce from that surface, we trace the ray to the sun, we compute light and shadow just as we've done before. You can see here it has a much larger impact on the scene, and it gives that scene that much more global illumination feel to it. Now we can actually repeat a number of these steps ad infinitum depending on how much recursion or how many bounces you want to do, and that's a trade-off between image quality and performance. The final step is denoising. For real-time rendering, we'll typically shoot a few to a few dozen rays per pixel. Denoisers take that relatively sparse sampling and then construct the final picture through a sophisticated combination of spatial and temporal processing. So now that we've gone through all the steps of building our path tracer for Quake II RTX, let's take a look at this in action. We're going to toggle back and forth between the original Quake II render and the new path trace Quake II RTX renderer. As you can see, the Quake II RTX render has much more realistic lighting, it has that global illumination feel to it, it has reflections, refraction. It's just a much richer experience than the original Quake II. To give you a feel for the computational power required to do this, let's dive into a data capture of a single frame from Quake II RTX. What we've done is use our performance analysis tools to capture and analyze the frame. The topmost graph that you see there is a GeForce GTX 1080 Ti, and you can see there's a long horizontal section there, and that's that ray tracing and path tracing being done entirely in software. The next chart down is the same analysis, but based on the Turing architecture. So we're using a GeForce RTX 2080 in this case, running again ray tracing in software. So the graph that you see there shows two different colors, one of them integer and one of them floating point, and that's to show the benefit of that simultaneous integer and floating point execution. The final step, of course, is to run ray tracing on the RT cores. So again, using the same RTX 2080, the green you see here is the ray tracing execution being done on the RT cores. Comparing that to an RTX 2080 without RT cores, it's about 3 times the performance. And then comparing that performance to a Pascal, a 1080 Ti in this case, it's about 6 times the performance. So what we have here is a deep dive into the actual workloads that are being computed on the GPU. The first step is constructing the bounding volume hierarchy. This is kind of an acceleration structure where we take the geometry from the scene, the raw geometry, and put it into a form that's efficient for ray tracing. The second step is to compute the primary rays. And you can see this is not a huge workload on the scene. This is something that could be done in rasterization, but we've chosen to do in our pure path tracer. After that, we then move on to the direct light. So this would be reflections, refraction, and direct lighting. This is about 20% of the frame. After that, we move on to the indirect lighting calculations. The slides that we just walked you through were actually showing the first bounce, but I did mention that you have an optional number of iterative bounces after that. So what we've done here is captured a trace that has a second bounce. The incremental cost is fairly expensive for that indirect lighting. In fact, it's about 1/3 of the total frame time. The final step is denoising. That's taking that grainy image and then resolving it to produce the final image. What we're showing here is the two kinds of denoising being done in the GPU, both spatial and temporal processing. Post-processing produces the final results for the screen. This would be things like motion blur, depth of field, and bloom. This consumes about 10% of overall frame time. We've really enjoyed bringing ray tracing to a venerable classic like Quake II. As an added bonus, all the toggles that we use to turn those effects on and off in the game, we're going to ship with those so you can play with them yourself and see what ray tracing does for you. Thanks for watching.